Transmission lines and health. Currents in DC transmission lines can be 100 amps or higher. Some people are concerned that the electromagnetic fields from such lines near their homes could pose health dangers. For a line that has current 150 amps and a height of 8 meters above the ground, what magnetic field does the line produce at ground level? Express your answer in Teslas and as a percentage of the Earth's magnetic field B Earth, which is 0.5 Gauss. Is this value cause for worry? Here is a transmission line. The current passes from left to right. Using the right-hand rule, our thumb points in the direction of the current, right-hand thumb points in the direction of the current. The four fingers curl in the direction of the magnetic field. You can see that the field is coming out of the page here and going into the page here. So it's circulating like this. And I define the radial distance r from the center and the angle theta with respect to the horizontal. Okay, so for this transmission line, we can write Ampere's law states that the closed path integral magnetic field dot product with the small differential length element dl is equal to mu0 permeability of free space times the current enclosed by the path. So that's Ampere's law. Now, if I apply this law to this case, you can see that this is the current I enclosed by this path. That's the magnetic field circulating around it. So using the right-hand rule, I found its direction. So here is my radial distance r from the center of the transmission line, and here is the angular displacement theta. Now, in order to perform Ampere's law, I have to find this differential linear element dl. Now dl is r d theta in theta hat direction. So theta hat direction is the direction of the magnetic field, and therefore I'm defining my dl in this direction. So this is my dl on which I will perform this integration. And the magnetic field direction was found using right-hand rule is B in theta hat direction. It is found using right-hand rule, and it's only a function of r. Okay? Now, according to Ampere's law, the closed path integral B dot dl, because the dl vector and magnetic field vector are parallel to each other, the dot product gives me b dl, and because the magnetic field is constant as a function of, it's just a function of radial distance r on this path, the magnetic field magnitude is a constant, it comes out of the integral of dl around this circle is just 2 pi r. So b times 2 pi r is mu0 permeability of free space times the current enclosed. Current enclosed is equal to I. So the magnetic field created by this wire is mu0 times the current I divided by 2 pi r, and this is for r outside the wire, of course. So we are outside the wire. Okay, so r is greater than r wire, outside. So in this case, what is our radial distance from the transmission line, it is h. So we're concerned about being a distance h from the center of the transmission line. So I'm going to set r is equal to h and check for the magnetic field generated by the wire, for it not to be worrisome. I compare it with the magnetic field B at r is equal to h. This should be much less than the magnetic field created by the Earth's magnetic field. So my requirement is that mu 0I divided by 2 pi h should be much less than the Earth's magnetic field, and that means the current should be much less than 2 pi h times Earth's magnetic field divided by mu 0. So that's a requirement so that we don't consider any health issues created as due to this magnetic field. Okay, so if I calculate this magnetic field generated by this wire, it is B is equal to permeability of free space is 4 pi 10 to minus 7 Henry per meter times the current is 150 amps divided by 2 pi h is 8 meters, and that gives me a magnetic field magnitude of 3.8 micro Tesla. So that's the magnetic field I have at the ground level due to this transmission line. Now, if I compare it to Earth's magnetic field is 0.5 Gauss, and 1 Gauss is 10 to minus 4 Tesla. So magnetic field of the Earth is 0.5 times 10 to minus 4 Tesla, which is 50 micro Tesla. Okay, so if I write the ratio of my magnetic field B to Earth's magnetic field, B Earth, and multiply it by 100, I will obtain 3.8 divided by 50 times 100. It is 7.6% of the Earth's magnetic field. Alright, so it's quite clear that this magnetic field is very small. So my conclusion is that since the magnetic field at r is equal to h, that's at the ground level, is much less than the Earth's magnetic field, this value is not cause for worry. It's not worrisome. So that's my conclusion. For this problem. Okay, so I've looked at the magnetic field generated by a current carrying transmission line at a distance h from its center, so at r is equal to h. I have defined r from its center, and with the right-hand rule, I can see that the magnetic field is circulating around this transmission line in this sense, and when I perform Ampere's law, the closed path integral b dot dl gives me b times 2 pi r, which is mu 0I enclosed. Mu 0I over 2 pi r is the magnetic field outside the wire. When r is equal to h, this tells me that the current should be much less than 2 pi h magnetic field of the Earth divided by mu 0 for it not to be worrisome. When I calculate the magnetic field generated by 150 amps transmission line at a distance of 8 meters from the ground, I find 3.8 microtesla, which is much less than 50 microtesla, the magnetic field of the Earth. Therefore, this value is okay for health.